So I am working with multiple papers all simultaneously because that's how life is as a professor. And I was looking at one today that is almost ready to be submitted, and I had not looked at the paper since March, like the Friday before, like we closed down for the pandemic, which just tells you how much like work a person can get done when you have like an 18-month-old at home. I hadn't looked at it until today, and I opened it, and I was reading through things, and I had no idea where I had stopped. I was having to read to be like, what does it look like? Looks like things that I have written versus what the original copy of the thesis that my student wrote was. It's a pretty distinct difference in our writing styles. That part was pretty obvious. But of course, the thesis was done like 3 years ago. And then I'm having to read our stats and things, and I'm looking at our graphs, and I'm like, I don't understand. Like, I don't know which graphs I'm supposed to be looking at and which ones are right. And so that was my pitch to all of you, especially Callie and Megan, since they're doing their thesis, to please do everything in your power to get your stuff as close to ready for publication as humanly possible so that you don't leave your poor advisor 2 years later like me wondering what graphs go where and what these little things on the graphs actually mean, because they're slightly different than yeah. So I'm like, okay, this has been fun for me today. So now I have to start not all over again, but I have to go back and like reread a bunch of stuff tomorrow and pull up all of the data and pull up all of our statistics and like try to figure out like, okay, well, this thing is a significance mark here and there, but is noting this or anyway. So don't do that, and then don't sit on things and not look at it for 6 months or 7 months like me either. That's also not the way to do things. So have your stuff in a better place than me. That's all I'm going to say. Do as I say and not as I do. That's your advice from Dr. Black. Okay. Alex, you ready to teach?
Oh, yeah.
Jacob has today?
I had last time.
You had last time. We could do it like law school, or like we're just going to do a little, like Socratic method, like, tell me about the cardiac cycle today. Like, what does this mean and what's that? So, okay. So we've begun kind of talking more so about the cardiovascular system, right? A little bit of anatomy last time. We went through the cardiac conduction system, so we were discussing the movement of an action potential through the chambers of the heart and how that's going to lead to a cardiac contraction, which will become very, very important after the next couple of slides. So to me, the next thing that we need to get into and understand is something called a cardiac cycle. So a cardiac cycle is one heartbeat, okay? What it really is it's the events that are occurring during a heartbeat, okay? So when the heart contracts, each individual chamber, so each of the 4 chambers undergoes a period of time that is called systole and a period of time that is called diastole, okay? This is why blood pressure is measured as systolic over diastolic. Words were not chosen by James. So systole denotes the period of time when that particular chamber is actively contracted. Okay? Diastole is the opposite. It's the period of time during which that chamber of the heart is relaxed. In one cardiac cycle, so in the time it takes when your heart beats once, all 4 chambers will undergo a period of relaxation and a period of contraction. Okay? So the amount of time that each chamber spends in each one of those is going to vary, mostly due to your heart rate. Okay? So at rest, in a person that has a kind of a resting heart rate of maybe somewhere between 50 and 60 beats per minute, you're going to spend about 60% of the cardiac cycle is going to be spent diastole compared to about 40% in systole. So at rest, when heart rate is relatively low, more time is spent with the heart, chambers of the heart relaxed. This is going to become immensely important, okay? Because it's during diastole that particular chamber, and we're going to use the left ventricle as kind of our representative chamber. During diastole is when that chamber of the heart is able to fill up with blood, okay? And so it's like, in some ways, pouring, again, I'll use a baby analogy, I'm pouring milk into Ellis's cup. She has these little sippy cups now, okay? We can't wash them in the dishwasher because, of course, they're fucking made out of plastic. And apparently, if you wash things and you can't microwave them, you wash anything, I think it's all a conspiracy by the people that make aluminum. Now, you can't wash them, so guess what I spend all my time doing? That's right, washing these stupid cups by hand. She goes through a lot. I'm totally not. We have these like silicone, squishy silicone plates. One, if she throws them, they don't break. But two, you can actually wash them and all leach out. And then for school, she has water pumps like that are made out of metal. They're like those things that you don't carry around with your water all the time, which doesn't make a lot of sense to me. But apparently, they're metal. They were like $20 a piece. She has 3 of them. They have to wash that shit too. Sometimes the dishwasher's not ready to go. I only have 3 to school 5 days a week. There was a point to my diatribe. I'm pouring milk into her sippy cup. Okay? The longer the amount of time that I'm pouring milk in, conceivably, the more that's going to manage to fill up into the cup. Okay? If I only pour for a short period of time, I've got to pour it more vigorously or at a higher kind of tilt thing. Same thing's going to happen in the heart. We're going to be in a place where the longer the heart is relaxed, the longer that chamber is relaxed, the more blood is flowing. That's going to end up being a positive thing for us. So this change in the time spent in diastole versus the time spent in systole is going to alter itself around with exercise. It's going to change as a consequence of chronic training at rest. It's going to have these very profound impacts on cardiac output, especially on okay? So that's the long story of why we need to care about this. At a resting heart rate of about 75 beats per minute, which no one is probably at about 75, but this is roughly what you would get if you had no sympathetic or parasympathetic input on the SA node, about 75 beats per minute. It's about 0.8 of a second, okay? So of that 0.8 of a second, you're going to spend about half a second in diastole and about a third of a second. Okay? And then we found it, and now it's gone again. Oh, we did it. Which one of y'all did it? We're just taking the thing. That's some not good stuff. Okay, well, so this thing will continue to not work, so I'm going to have to not even sit. This is just showing this relationship between systole and diastole, so it's showing the relative length and time that each one of them are going to occur. But it's also showing the relative time spent in each, okay, as it's going to work. So what happens is, as heart rate increases, say during exercise, if you were me this morning trying to run my fat ass up the hill from down by the tennis courts up here to the building to finish off my run, then I'm probably not, I don't even know if I can get to 180 beats per minute. Age predicted max tells me that I can't, but I was probably pretty close to that. As that goes up, you'll note that we've gone down to there's about a third of a second for each heartbeat, and we have compressed. So systole has lost some time, diastole has lost some time, but I want you to look at that we've lost a disproportionate amount of time spent in diastole. Okay. some instances with some people that can become a problem. Okay. So another thing surrounding the cardiac cycle is something called an EKG or an ECG, otherwise known as electrocardiogram. Okay. I'm not going to show you guys one of these. You're not going to have to identify all of the different waves. You're not going to have to identify pathology from these different kinds of waves. But an ECG or an EKG is a printout of the electrical activity of the heart. Okay, it looks like this. And so you have a P wave. You have this then followed by a QRS complex. You have this S to T segment, and you have a T wave, and then we start over and we have the next cardiac cycle. Okay, so this is simply a way that we put electrodes on your chest around your heart. Okay, and we can measure the movement of the action potentials in the heart. Okay. And so each individual wave is going to denote a particular electrical event that is happening in cardiac muscle. The P wave, which is first, is going to denote the polarization of the atrium. The QRS complex is going to denote the depolarization of the ventricles. And then the T wave denotes the repolarization of the ventricles. Don't ask me if it's repolarizing, why it doesn't come down. I don't know. Okay, that's always bugged me. Why is the T wave not inverted? I'm not sure. I need to call a cardiologist. I'm sure it's very. I just asked Dr. Larson for a very obvious reason, but I'm sure it bugs me. You will note that you don't see a wave that denotes repolarization of the atrium. That's because it is subsumed by the QRS. Okay. Now, if you have problems with cardiovascular function, especially if you have problems with cardiac conduction due to a lack of oxygen in the heart, likely due to blockages in the coronary arteries, you get cardiac ischemia, then these waves, this conduction is going to change in a relatively predictable manner. Okay, that's going to be this is one of the most useful diagnostic tools for seeing if people have ischemia to their cardiac tissue. And so because of all of that, what do? They think somebody has a heart attack, you show up at the hospital, and they throw your ass on the treadmill. And they say, go, we're going to try to induce another heart attack. Well, they've got you there because they want to see, can they see some abnormality on the EKG that will tell them we've got ischemia in the right ventricle from the right circumflex coronary artery. And so that's what we need to try to target to do bypass surgery. You can use this because there are multiple leads. You can pinpoint it down to which chamber, is it dorsal or ventral, and things like that. Okay, that's the purpose of it. Now, if you're really a glutton for punishment, which maybe those of you guys that are in Dr. Kellerman's lab, this seems like something that would be right up y'all's alley. Okay, I think I borrowed this from my graduate class in. We didn't have human physiology. We took animal physiology in the vet school at Georgia, and it was all basically the same, except we had to do reproduction and we had to learn why they put the sheep in the back of the truck together. And I'm not kidding, that's a real thing, right? Like we talked about, it's because of the hormones and the union close in proximity and all that. It makes a lot of sense. But what you can see here is systole, diastole, systole again, so you can see, okay, you can see the cardiac cycle. What you're denoting here, these are going to be sounds that you can hear if you were listening with a stethoscope. And then it's going to show the changes in pressure, okay, pressure and the changes in volume inside all of this. So you can track from all of this the aortic valve opening, the atrioventricular valves opening and closing. You can track the actual physical events, the electrical events, the sound events, and in some ways the movement of blood that's moving all the way through all of this. Okay? Again, you don't have to know this. I'm not going to ask you about this. Okay, was that your question, Alex?
I do have a
Okay, you don't, I just am putting it here because it's a grad class and it may be of some use to you at some point. If only because maybe you're going to teach one day, you're like, that's right, I'm going to throw that shit in there. Dr. Black showed it to us and it looked really cool and complicated. I'm going to show it to my students. Be like, look at all this stuff I could have you guys try to do. Okay? Here we go. Understand, Jacob? Yes, pay it forward. Okay? Now, Alex, you have a question.
I do have a very specific person. How does it change if a person has a low ejection fraction? We talked about ejection a little bit, but I have no idea how to impact that.
So all that you're showing, like, is it's just denoting that at this particular point, when pressure rises to here, you're going to get ejection from the left ventricle into the aorta. So my guess is where you're going to denote things is that the aortic valve is probably going to open at the same time, but the issue with people that have low ejection fraction is going to be one of two things. It's either going to be that this pressure inside, right, into the left ventricle is not going to rise as much, or therefore you have like you have congestive heart failure, you have normal aortic pressure, but the left ventricle is so weak that it has a hard time properly overcoming that aortic pressure, or much more likely you have elevated peripheral blood pressure. So aortic pressure is higher than usual. You're hypertensive. Therefore, you've got to raise the pressure inside the left ventricle, not to 120 to get blood to eject. You've got to raise it to 200 or something like that. That would be my guess, is that this would shoot up higher in those ways, but unless you have congestive heart failure. A lot of people that have congestive heart failure also have high blood pressure, so they're kind of doubly screwed. And right about at this point, Pearson is like, what the hell is Dr. Black talking about? None of this stuff makes any sense to me. I don't even know what is ejection fraction, what is any of these things. So we'll get to a little bit of that here, so don't worry. Okay. Or for the rest of it. Right? Did I answer your question? A little bit? Okay. So this would not necessarily be the best graph and the best way to try to figure out what's happening with ejection fraction. That's all I wanted to say.
No, it was related to, I didn't think it was and that was one thing that everyone was like, don't worry about that. No, that's wrong.
No ejection fraction is a problem clinically. It's a big problem. So, okay. To get at what that is, look, ejection fraction, right? So here it is on this slide. So what we're going to talk about next is during a cardiac cycle. Okay, you've got a heartbeat. The point of the heartbeat is that we want to eject blood or send blood out of the heart through the aorta out into systemic circulation. Okay, the amount of blood that is ejected from the left ventricle during its period of systole is a variable called stroke volume. Okay, stroke volume. All of the cardiovascular variables that we're going to talk about, you can make an argument, okay, that as it relates to exercise, as it relates to training responses to exercise, and those kinds of things, that stroke volume is the most important one because it's the one that can change. Okay? And you'll see why in a few slides. Okay? So in a kind of typical average sized person, stroke volume is somewhere around 80 milliliters of blood every time the heart beats at rest. Okay. I jokingly asked this question in my undergraduate class. For the first time, everyone looked at me like I'd finally grown a third arm. How many of you have ever used a camera that takes real 35 millimeter film? A camera that has film in it. You guys have? Not a Polaroid. No, no, no. When you have to like have the film, you're going to take the film to like Walgreens, they develop it for you and those kinds of things. So here's what happens. Okay, back in the olden days, which were not that olden days. I can remember when we bought our, we got as a wedding present, we got a cutting edge digital camera as a present to take with us on our honeymoon to be able to take pictures and do things, right? And it was outrageously expensive at the time, and it takes pictures that are about as good as like what an iPhone 4 would take or something. We're on like iPhone 12 or something, right? You know, it was like a 3.5 megapixel camera. So it's a pretty shitty front-facing camera picture on your iPhone. Okay, that's how far we've come in 17 years. Okay, you used to take pictures with this camera. It had film in it. You couldn't see the picture right after you'd taken it to know if it was any good or not. You had to wait. You had to go in a dark room. My wife had a class in college, a photography class. You had to take pictures and develop your own film. You could go in the dark room and wash it with like 14 different solvents and things, and you develop pictures, and you could look at them and you have negatives. If you had the negatives, then you could get more things, but you couldn't expose them to light. Okay? And so because of this, you would get the camera and you would get the film. You would put the film in the camera, but the film would always come in these little black canisters that had a gray top on. Okay? Those black canisters hold about 80 milliliters of fluid. And so I either need one of those or I need a new analogy because now apparently no one knows what the hell I'm talking about. Right? When I started teaching exercise physiology to undergraduates in like 2005, that was a really great thing because most of them were like, ooh, a digital camera, that's really fancy. Like, I got a real thing here. Okay? That's about 80 milliliters of this. Okay? It's about 80 milliliters. Look at this. There's 355 milliliters in a 12-ounce can. So that's like about a little under a quarter of a can. So it's not that much. We can calculate your stroke volume in this weird manner that most people that I find don't talk about this anymore. Okay? So stroke volume is blood that's ejected. It is the difference between something called end diastolic volume and end systolic volume. End diastolic volume is the amount of blood in the left ventricle at the end of diastole. So this is the heart, the left ventricle is relaxing, it is filling up with blood. This is how much blood goes in right before it's in there, right before it goes to contract. Okay? I've got this. I have this thing of hand sanitizer. This is my left ventricle. Okay, here would be my left atria. I'm pouring, it's filling up, it's filling up, it's filling up. It reaches at some point. At that point, then I squeeze. Okay, and so the total amount that's in there, right before it begins contracting, is called diastolic volume. Then I squeeze, and some squirts out. Then I relax again. Okay? When I relax, right there at the very end, or right before I relax, at the end of systole, most of the time, especially at rest, you're not going to eject all of the blood out of the left. There'll be some left over. So if I know how much was in there when it started, I know how much is in there when I'm left, the difference between those two things is the amount that was ejected. Okay? So stroke volume is the difference between end diastolic and end systolic. Ejection fraction, which Alex was talking about just a few minutes ago, is the percentage of end diastolic volume. It's basically stroke volume as a percentage of end diastolic. Okay? And so at rest, stroke volume, we tend to have an ejection fraction of about 67%. So that means that about 2/3 of the blood in the left ventricle leaves every time the heart beats. Okay? If I have congestive heart failure, I have low ejection fraction, this number is going to dip. And there are numbers for what is a clinically low amount that I'm putting off the top of my head, but it may be down number, it's pretty low. When we exercise, okay, if we have proper cardiovascular function, we exercise, this number is going to tend to go up. Okay? Ejection fraction is going to increase, which is a good thing. Okay? That's going to be a good thing. So we've talked about cardiac cycle, right? That's a heartbeat. Heart rate is the number of times the heart beats in a given period of time, so we put it in a minute. Stroke volume is the amount of blood that leaves the heart every time it beats. The product of those two things is something called cardiac output. Okay? Cardiac output is the amount of blood ejected by the left ventricle in 1 minute. Okay? You can pick any other frame of time if you wanted to, all of the math works out. That's what cardiac output is. Cardiac output is abbreviated as Q. I have no idea why it's Q. Jacob, you know?
Yeah,
It's just always been Q. Probably because, like in Latin or something, you know, right? Like in Latin, cardiac output is used to be, I don't know, something like that. Okay. So cardiac output, stroke volume multiplied by heart rate. At rest, okay, cardiac output is normally somewhere between maybe 4 and 6 liters of blood per minute. So you are circulating 4 to 6 liters. So like 2 or 3 of those 2-liter bottles of soda are moving around per minute and moving through your heart. Right?
How much is the total blood volume in the body?
Yes, it's a great question. That was my next thing. I was going to ask you guys. Guess what is also somewhere between about 4 and 6 liters? Your total blood volume. Okay? So in an average person with normal cardiac function at rest, you are going to circulate pretty close, give or take, all of the blood in your body through your left ventricle 1 time every minute. Okay? 1 time every minute. Blood volume and cardiac output are related to heart size, which is related to body size. So it tends to be a little bit lower in women than it is in men. Blood volume and heart size tend to be, per your body size, tend to be larger in people that are highly aerobically trained. So their cardiac output can be a little bit higher. So it's about 4 to 6 at rest. During exercise, that may go up maybe 4 or 5 times. Okay, it may get to, in a regular person, to about 20 liters per minute. In a very, very elite athlete, it may get up to like, somewhere between 30 and 35 liters per minute. You guys will see as we move along. Cardiac output, its changes during exercise, is directly related to and therefore directly predictive of energy expenditure and oxygen consumption. Right? We can add another parameter. This is how much blood we can circulate. We then have to figure out how much we can extract, how much the mitochondria can take in. But in essence, if you were to graph VO2 as you're working your way towards max cardiac output, changes like in a very linear manner. Right? So the larger your maximum cardiac output, in general, the higher your maximum VO2 is. Okay? So elite athlete, big cardiac output, much more fit, much higher VO2 than these people. Right? Here, average VO2 is like 35, almost double that, right? VO2 is 7. So it's not exactly 1-to-1, but that's kind of how this goes. Okay. Certain of you look very sleepy. Do we need to get up and do some squats in order to wake you up? You want to watch someone else do squats? Right? If you look sleepy, should I have one of the non-sleepy folks do that so you guys are no longer sleepy? No? Okay, so now that we know what cardiac output is, we know that it's going to change during exercise. It's going to go up as we exercise. Okay? I need you all to understand kind of as I go from rest to walking to jogging to running very fast, you need to understand the underlying physiological factors that are changing, that are going to lead to the alteration or the increase in cardiac output. Okay? And conversely, we need to understand that at some point, these factors can no longer change anymore, or they may change in a negative way, and that is going to set the top end limit of what our maximum cardiac output is going to be. Okay? So we're going to break these things down. Okay? And so we're going to start out with one of the things that contributes to cardiac output, and this is the much more simple, okay, is heart rate. So maximal cardiac output is maximal heart rate multiplied by maximal stroke volume. So if I want cardiac output to go up, I can do something very, very simple, right? Like we could just make a person's heart rate go up. We could ask Ryan to stand up on her desk and sing us a song or something, right? Or tell us about the worst date she's ever been on. Whatever, okay? Anything that might evoke an increase in heart rate is going to make cardiac output go up, okay? So we need to understand then what are the physiological factors that help us control and regulate heart rate. How might we make that either go up during exercise or during times of stress? How might we make it go down at rest, or things that we can do to make ourselves alive? Okay, so resting heart rate is going to be somewhere in general between about 60 to 80 beats per minute. You can truly get a person calm. Okay, and by calm, I mean put them in a dark room, have them lay down for a half an hour, listen to, I don't know, like rain sounds or something very calm and very soothing. Okay? In very highly trained people, so you have very high VO2 max, very aerobically metabolically trained, it may fall down into the 30s or 40s, maybe even into the high 20s. Okay, so resting heart rate also tends to be predictive of VO2 max. Resting heart rate is predictive of large cardiac output. Okay? If you're sedentary, it may be over 100 beats per minute. If you're a person that has low ejection fraction, it's likely to be very, very high as well. We'll talk about that. Okay? During exercise, heart rate tends to increase in direct proportion to exercise. So heart rate increases in direct proportion to change in oxygen consumption. I need more oxygen in my muscles, so I must make cardiac output go up to bring more oxygen. And one of the things that happens is that there's a corresponding increase in heart rate. Okay? That's why using heart rate, any of you that have like an Apple Watch, we could have Kelvin pull up something on his watch right now, and you can use heart rate as a surrogate measure to estimate exercise intensity, okay, without ever having to measure VO2. It's a good, easy way, it's relatively inexpensive now for us to guesstimate energy expenditure, percentage of VO2, and track that during exercise with our exercise prescription. Okay? The other cool thing about heart rate that we will talk more about is that heart rate changes very rapidly. Okay? If you change intensities of exercise, it goes up quickly and it will plateau very quickly. All right? So if we had Pearson get up and start doing some jumping jacks for us, his heart rate should go up almost immediately, right? If I had you guys like checking things, we had Keldon had his up. I could make his heart rate go up just by saying, Keldon, you're going to have to exercise in 5 minutes. It's called an anticipatory increase in heart rate. You suggest to someone they're about to exercise, right? If we had an exercise bike or a treadmill here, we could have Keldon get up, stand on the treadmill. Just stand on the treadmill, and his heart rate goes up. Okay? It's anticipating that we're about to exercise. And then once you start going, whereas there's that kind of relatively slow increase, that lag in oxygen consumption that we've seen. Heart rate does not lag nearly as much. Okay? If work rate is constant, heart rate can get up and plateau very quickly, potentially within about 10 seconds. Okay? So just kind of keep all of that. Another thing to understand. Maximum heart rate is predicted very, very closely by your age. And this is important to understanding one of the reasons that heart rate cannot continue to increase. This is going to limit cardiac output and potentially reach max, is that there is an upper limit on heart rate. The easiest equation to remember for calculating age predicted max heart rate is 220 minus your age. Okay, 220 minus your age. Now this other equation, 206.9 minus 2/3 of your age. For scientists, we're never happier than we're taking a perfectly good thing and trying to parse it down into something that is like 0.25% better in this one specific population or something else, right? It's what we all do. It's fine. Okay. I don't ever use this one. Maybe it's slightly like infinitesimally better, but I can't ever remember any other this perfectly fine. Okay. So all of you guys take 220, subtract your age from it. That's your age predicted maximum heart rate. Okay. You guys are probably 22, 23, 24 years old. So you guys are going to be somewhere in the high 190s, right? That's your age predicted maximum heart rate. Me, on the other hand, mine is 178. Okay. So right there from all of that, you guys have another like 20 beats per minute of heart rate that you could increase your, use to increase your cardiac output above and beyond what I'm physiologically able to do. Okay. We'll talk about the thing that limits that in a second, but I can't do that. And so that's one of the reasons that VO2 max tends to decline with age. Okay, it tends to decline with age because it's just a physiological. Okay, Meg.
I was gonna ask why.
The SA node becomes less sensitive to epinephrine. Is generally what is the thought process behind it. There's maybe in some people some evidence that if you continue to train a lot, that maybe you are not going to have, you're not going to lose all of it, but in general, you still lose quite a bit. The video that I saw at ACSM meeting of like a 90-year-old, I think he was Finnish, like former Olympian. And he was on a bike and doing the VO2 max test. And he had an EKG, like they were all worried about that stuff. Like his VO2 is probably higher than my VO2 is right now. So he was just beast moding all over a freaking bike test, which you guys will get to do. It's so much fun. It is awful. Ryan, did you have a question?
It was just kind of a thought. It might hurt, but what actually like is something really bad?
Oh no, absolutely. No, nothing bad happens at all. It's just likely going to mean you're going to have to not be able to exercise. It's not like you die, your heart doesn't explode or anything else. And the age prediction is off a little bit. Like, I mean, we've done tests on people in the lab, especially when we were doing stuff with kind of involving time trial performance with caffeine, where it was not unheard of for us to have college age participants with max heart rates in like the low, like 220, like 212, 213, something like that. Okay? Not unheard of. We would have our undergraduate helpers be like, are they about to die? Like they're, but you know, if you give yourself something that mimics epinephrine and norepinephrine, like caffeine, you may be able to squeeze a little bit more out there. There's some weird evidence that like you take caffeine and your heart rate, it doesn't adversely affect your heart rate until you start exercising. So if you're on caffeine, your heart rate at any given work rate is going to be a little bit higher than exercise, but that has no effect at rest. Even if you feel jittery, it's like this weird thing. So how do we regulate heart rate? There's something called extrinsic regulation. Extrinsic means outside of the heart. Okay? So this is going to be primarily controlled by the autonomic nervous system. So sympathetic and parasympathetic nervous system to the SA node, okay, is going to drive this thing. so epi and norepi increase heart rate. Okay, so things that stress you out lead to the release of epinephrine and norepinephrine, which lead to this elevation of heart rate. It's part of the fight or flight response. I need to run away or I have to punch somebody, right? We're gonna fight off this, cheetah or something. Increase heart rate, increase cardiac output, so you're ready for it. Right? Raise metabolic rate, you can really do this. Conversely, parasympathetic input through acetylcholine is going to lead to a decrease in increased heart rate. You have a large number of both sympathetic and parasympathetic neurons that are going to connect to the atria, whereas the ventricles receive pretty much only sympathetic fibers. Okay, so what that means is that when we want to lower heart rate, we're going to primarily do that by removing the effects of epinephrine and ventricles and then applying acetylcholine on the SA node of the atria to slow things down. So remember, atria contract first, and those triggers from the atria having their signals get transmitted down to the ventricles. So slow the atria down, because there's no additional receptors in the ventricles, then they should follow suit. Okay? Whereas all of them are going to be sensitive to epinephrine. Okay? At the start of and during low to moderate intensity exercise, heart rate can, at the start, be increased simply by removing parasympathetic input. So if you imagine that your heart rate is controlled by this spectrum of all parasympathetic input on one end, all sympathetic input on the other end, and you're somewhere between those two things at all times. And so if you imagine that sort of this intrinsic regular fiber rate of the SA node is at like 75 beats per minute. As I drop parasympathetic on top of that, it goes down. Okay. If I then remove that parasympathetic, it's going to slide back up towards that kind of middle point, that 75 beats per minute. Then if I want it to go higher, I have no parasympathetic, then I begin to add sympathetic on top, it's going to start to go up. Okay. Does that make sense? That was a tricky thing for me when I was learning all of this to kind of appreciate. It's not like one does this, one does that, but you can remove something that kind of begins to. Okay? So it looks very much like this. This is a very old school graph of all of this. This point, like right here, okay, that may be about the intrinsic firing rate of this animal model, which is probably what it was. Jacob, it's at about 100, okay, which we talked about last week after class. But you've done input, so the parasympathetic nervous system, it's going to be input from the vagus nerve. Okay? That's vagus nerve, and then sympathetic is going to come in. It's going to raise things as we get up higher and higher towards maximal. Okay, so if you are a person, let's say you have high blood pressure, I'm going to give you a drug. Sounds like a Dr. Black question on the test already, doesn't it? I'm going to give you a drug, and it's going to block the effects of the sympathetic nervous system on cardiovascular tissue. Guess what? These drugs are super common. It's called beta blockers. Right? There are also alpha blockers, but they block adrenergic receptors. So you dump sympathetic nervous system input on the cardiac muscle, and it has a much attenuated effect. So you go to cardiac rehab, that a person is post-heart attack, they're hypertensive, they're on beta blocker, you put their ass on the treadmill, and they get to like 60% of their rated predicted max heart rate, and that's all they got, and they're done. And they're like, wait, like I'm not working that hard, like what's happening? It's because they cannot raise their heart rate anymore. They cannot induce that. So you've got to consider that these things exist. Okay? Or, let's say, rather than this, I'm just going to inject you directly in the heart with atropine. Okay, it's the Pulp Fiction one. Restart the heart. Jumpstart with some sympathetic nervous system. Okay. That's kind of what's good. Okay.
So, just a question. When it comes to synthetic and parasympathetic activation, are you saying that just for the heart it happens? So like just for the heart, it decreases parasympathetic first.
So if I understand what you're asking, then the first part of talking about where they're kind of changing parallel and inversely with each other is not my understanding of how it works. It's that you're getting input from one or the other, and that you're sort of driving yourself towards this middle point. And so I'm resting, I've got vagus input, I have basically no sympathetic input, right? And I've got vagus input that's driving me below my normal intrinsic firing rate. So then we'll go back to our example. We're going to have Ryan stand up and sing for us. She's going to immediately then clamp off the vagus signal, and then that's going to drive it right here very quickly. And she's probably going to put notes. So unless she wants to be a performer and singer, which some people do, then that's going to start driving the sympathetic.
So it's not like acronyms. Yeah, 95% of your system is working at parasympathetic, 5% is sympathetic, and then as it goes on, it's slowly.
I think that's it.
Yeah.
That's not my understanding, but that doesn't mean that that's not right. We need to ask y'all's boss. He might have a better thing.
Yeah, because I don't, maybe I'm.
That you may not be remembering that. I'm hardly like an expert in sort of sympathetic and parasympathetic input. But using this particular graph, which is why I use it, this is the graph that was used when I was taught. So we can ask. I want you guys to appreciate how it is. I understand. I know what you're talking about. But here is there's always a little bit of both. And here it's like 95 to 5, and somewhere in here we'll go. I got you. So, got it. So the other piece that we haven't talked about, so you will note that the sympathetic nerves are going to innervate in the visual. So when I give you epinephrine and norepinephrine, in addition to raising your heart rate, it also is going to increase the force of contraction of the left ventricle. Just so that as cardiac output goes up, blood pressure tends to go up. And we haven't even talked about there are going to be potentially some effects out in the peripheral materials that they can think about a blocker. That's going to cause epinephrine and norepinephrine tend to cause constriction of the peripheral blood vessels. And if they constrict, peripheral resistance increases, and so that means blood pressure is going to have to go up to overcome that resistance to get blood to a certain degree. And so that's kind of how it's going to work. You want to tamp down cardiac output. That lowers blood pressure, which also reduces peripheral effects. But now I'm questioning in my own mind, if you take a beta blocker, how much are you getting in one place versus how much are you getting out? How much of it is a peripheral effect versus how much of it is central?
Have those medications. I mean, obviously the goal is to cut them off of it, so then you're having an exercise, you want them to still like stay on it and like limit themselves to all the time.
So you want them to continue to exercise. By exercising, they can potentially then have cardiac hypertrophy, increase their stroke volume, and therefore increase their cardiac output that way. And they're going to get, as we will see later on, they're going to hopefully get both angiogenesis and atherogenesis, where they're going to get more peripheral arterioles and then get larger arteries and arterioles. And as they get larger, they will model get larger, and pressure inside of those will fall. And that's going to potentially be useful. The exercise is good. We want them to exercise. It just being on a beta blocker may just limit the top end capacity of them to exercise. So you have to strike that balance of maybe having them on some and do stuff to start with, get some adaptations. Okay, let me see what the next slide is. Maybe like one more. Again, we'll see extrinsic control of heart rate, and then we'll stop there. We'll pick up the really fun stuff next time we talk about stuff. Okay, so extrinsic regulation of heart rate. We talked about sympathetic and parasympathetic input. But there's also then going to be input from the periphery, input from blood vessels, from joints, and from muscles. You're going to have chemoreceptors and mechanoreceptors that are going to pick up changes in kind of the chemical environment and then actual changes from movement, which is what the joints are going to be. Okay. These signals from this are going to function to modify parasympathetic or sympathetic outflow, bring about the appropriate cardiovascular and the respiratory responses. Okay. So we'll talk about some reflexes that are related to some of this stuff driven by the barrel reflex, that's driven by the chemoreceptors and the receptors. Okay. That's heart rate regulation. All right, so we'll pick up with stroke volume next time. Right now, no. We will talk about some more specific ones a little bit later on. That seems very un-me, right? To do something like that. We're talking about all these changes that make an enzyme go faster, and you're mentioning receptors, and not saying, oh yes, they're sensitive to oxygen, carbon dioxide, hydrogen.